Let's say you have an atom of uranium, maybe uranium 2, let's see, that would be uranium 238. And you want to know, all right, if this thing decays, will it become stable? And the answer to that is both yes and no. If it decays, it will become stable, but not after just a single decay event. If you have a really large atom like uranium, a single alpha decay is not going to get in anywhere near a stable isotope. Because if you remember, nothing bigger than bismuth, which has 83 protons, is stable. Uranium has 92 protons. So it is going to take a lot more than just one alpha decay to get this down to the point where it even has the possibility of being stable. And remember, I said that 83 is the largest number of protons that could be stable. That does not mean that if you have 83 protons, you are stable. There are quite a few isotopes of bismuth that are unstable. There's actually only one, I believe, isotope of bismuth that is stable. So it's not just good enough to get down to 83 protons, you have to have the correct number of neutrons as well. So if you have something like uranium 238, it's most likely, in order to become stable, going to go through a whole series of radioactive decays like this one that we see here. Now this is not the same radioactive decay that every uranium 238 is going to go through. This is a very common one, but there are possibilities. There are different ways it can do this. You could have the same number of overall decays but in a different order or something like that. But this is one possible decay series for uranium-238. And as you can see here, in order to become stable, this uranium undergoes an alpha decay, which is the blue line here, 2 beta decays, 1, 2, 3, 4, 5 alpha decays to get down to lead, which you would think, okay, it's down to lead now, it should be stable. Nope. It is lead, but it's not a stable isotope of lead. Again, lead, while it does have some stable isotopes, there are lots of other ones that are unstable. So it needs to undergo 2 more betas, another alpha, 2 more betas, and then finally it gets to a stable isotope of lead. One of the reasons that I'm bringing this up here is because there's going to be at least 1 or 2 questions in the homework where they give you a radioactive series like this, or they ask you to figure out a radioactive series like this. And the way those are usually phrased is they'll give you a starting isotope, like uranium-238, and they'll ask you to figure out how many alpha decays and beta decays does it take to get to this final isotope of lead-206, for example. So without even seeing this, we can actually calculate how many alpha and beta decays it takes to get from here to here. So if we just ignore this for a minute, so let's cross all that out. We don't know what's going on here. We have no idea how many of what is happening. We just know we're starting with uranium-238 and going to lead-206. The way we can figure this out is because we know we started with a mass number of 238, and we know that we end with the mass number of 206, we lose 32 mass, going from here down to here. So even though we have no idea what's happening in this whole process in the middle, we know going from here to here, we lose 32 mass. And if you remember, there is only one way to lose mass, and that is alpha particles. So if we lost 32 mass, and every alpha particle has a mass of 4, that means that even though we have no idea what happens in the middle here, we know that it takes 8 alpha decays to get from here to here. We don't know what the order is. We don't know if we do 3 alpha decays and then some beta and then some more alpha. Like we don't know. We just know in total it takes 8 alpha decays to get from the starting point to the ending point. Once we know that, we can use that information to figure out how many beta decays we are going to need. Because if we start with uranium, which has 92 protons, and we end with lead, actually let me back that up for just a second. We're starting with uranium, which has 92 protons. We were losing 8 alpha particles, each of which have 2 protons. That means we're losing 16 protons from the alpha decays. And 92 minus 16 is going to be 76. Am I doing that right in my head? Let me just double check to be sure. 92 minus 16. Yes, 76. So from the alpha decays, we will be down to 76 protons. But we need more than 76 protons because we know that we end not with 76, we end with 82. That's the atomic number for lead. So our end point has 82 protons. Taking the alpha decays into account, we only have 76. So we need 6 more protons, and those are going to come from those beta decays. Because remember, beta decays turn neutrons into protons. Beta decays will not change the mass number, so we don't have to worry about that. Our mass is correct. The beta decays are just going to turn some of the extra neutrons that we have into protons to get us to the correct number, which is 82. And so you're going to do a similar process in a couple homework questions, where you're given a starting point and an ending point, and your task is to figure out how many alpha particles, or how many alpha decays and how many beta decays did it take to go from one to the other. And so you'll just do that exact same process that we just did here. Which, at first it seems, how in the world can I tell? We're not asking you to write out the whole series. We just want the total number. How many alpha particles, how many beta particles. A few other miscellaneous things here. These are some tools that will help us to figure out if an isotope is stable or not, even without knowing where it sits on that valley of stability. There are some values, some numbers of protons and neutrons that, for some reason, seem to be more stable than others. So nuclei with 2, 8, 20, 28, 50, or 82 protons, or with 2, 8, 20, 28, 50, 82, or 126 neutrons, tend to be more stable than nuclides with a different number of nucleons. These have been given the name magic numbers because for a while it was not understood why those specific values of protons and neutrons are more stable than others. I believe we don't know 100% sure at this point, but I believe the best going theory is that the nucleus has a structure just like electrons have structures. And if you remember, there's certain numbers of electrons that are stable because that gives the atom a full valence shell. Kind of similar to that, there are certain structures of the nucleus that are stable. And so having those numbers of protons or neutrons makes the isotope more stable. So those numbers of protons and neutrons are more stable. In addition to that, nuclei seem to like even numbers of things. So nuclei with even numbers of protons and neutrons, or even just even numbers of one or the other, tend to be more stable than nuclei that have odd numbers. So the number of stable isotopes that have even numbers of both protons and neutrons is 157. When you get to having an odd number of one or the other, there's still a decent number. There's 53 that have even numbers of protons but odd numbers of neutrons, and there are 50 elements or 50 isotopes where you have an odd number of protons and an even number of neutrons. But when it comes to isotopes where you have an odd number of both, there are only 5. 5 isotopes in all of the known universe where you have an odd number of both protons and neutrons and the thing is still stable, which is just mind-boggling to me. It's amazing. And I believe all 5 of those are within the first 10 elements of the periodic table. It's all very, very small isotopes. But I could be wrong about that. You should double check me on that. But you can think of things like lithium, for example. Lithium, if you remember on the table, it's element number 3. It has 3 protons. It's an odd number of protons. And if you were going to base how many neutrons it was going to have based on the elements around it, you would think that the most stable isotope would have 3 neutrons, but no, it has 4. If you look at the periodic table, the mass number of lithium is 7, because it has 4 neutrons in this most stable isotope. I'm not entirely sure if lithium with 3 neutrons is stable or not. I'd have to look that up, but I know for sure the most stable, the most common isotope of lithium has 4 neutrons. So it has that even number of neutrons, which is kind of strange, and honestly I have no idea why this is the case. Maybe someone somewhere does. I have not looked it up at some point, but I do expect you to know that the nucleus likes to have even numbers of protons and neutrons if it can manage it. It is sometimes okay to have odd numbers of 1, but rarely is an isotope stable with odd numbers of both. And we can see that here, by the way, in this figure. So the blue elements are elements that have 2 or fewer stable isotopes. And then the orange, or kind of pinkish salmon color here, those are elements with 3 or more stable isotopes. And you can see that it almost perfectly follows odd, even, odd, even, odd, even, going across the periodic table. There's just I think just 2 exceptions here, which would be carbon and beryllium, which should have had more stable isotopes, but only have 1 or 2 in the case of carbon. And it is saying here that lithium has 2 stable isotopes, so I bet lithium-6 is stable. It's just not very common. Looking over this table, by the way, can you find the element with the most stable isotopes? There's a few that have a bunch. Like you can see, ruthenium has 7, molybdenum has 6. Xenon has 9 stable isotopes, but the largest number of stable isotopes goes to tin. Tin has 10 stable isotopes. And this is largely because it has a magic number of protons. Remember, 50 was a magic number. Tin has 50 protons, and so it automatically will always have, at the very least, not only an even number of protons, but a magic number of protons as well. And so you have quite a few stable isotopes for tin. Alright, I think we'll leave it there for this video. In the next one, we'll start talking about naturally occurring background radiation and how all of you are getting your daily dosage of radiation. So I'll talk to you in the next one.